There's about 1,000 problems that I already did. This is check if there's a valid path in a grid. Okay. So you are given an M by N grid. Each cell of the grid represents a street. Interesting. The streets of the grid can be as follows. 1 means that a street connects the left cell and the right cell. 2 means the street connects the top cell or the upper cell with the lower cell. 3 means that the street connects the left cell and the lower cell. 4 means that the street connects the right cell with the lower cell. 5 means what? 5 means the street connects the left cell with the upper cell. And 6 means that the street connects the upper cell with the right cell, or the right cell and the upper cell. So interesting, right? So each grid item, right, each cell within the grid will give you one of these 6 options, and they correspond to one of these 6 streets. So looking at a grid like this, right, if you have the grid 2, well, then 2 would mean this street. 4, 3, 6, 5, 2, right, because those are the forms of the streets that are here. So you just look at these grid cell items and you replace them with their corresponding street. You'll notice that you'll get different sets of paths, right? Depending on the street type that's used, you may get a connection, right? For example, 6 and 5 can connect to each other, right? 6 and 5 can connect to each other. 6 comes before 5 because 6 can go here, connect here at 5, and go up, right? So here you see that connection. Versus you could have a street set up like this, where the placement of the streets don't lead to actual connections between cells, right? Because since 1 is here, you can go from left to right, but 2 goes from bottom to top, so they don't actually have an opportunity to connect, right? I can't connect to this cell from this cell because there's this space here, right? I can connect from this cell downwards, but this is a dead end at this place here. So basically, for each cell, for each street type, there's different streets that you can connect to, and there's different streets that can connect to you, right? There's that kind of relationship, right? Like, for example, street 1 could connect to street 3, it could connect to street 5, going from left to right. Versus, street 2 can't connect to street 1, but street 2 could connect to street 6, right? If you went down, you could connect to street 6. You can kind of imagine that. So that's kind of an interesting component of this problem, right? When you're at any cell, you have to consider what the kind of street type is that you're at, what direction you're trying to go, and what you'll be able to connect to. What different kind of streets you connect to check if you can connect to your neighbors. Okay, so in this problem, you're going to start at the street, the upper left cell. So you're going to start at position 0, 0, so the top left corner. And a valid path starts from that cell, and it's going to end at the bottom right. So a path should only follow the street. So you have to be able to actually use the street. You can't jump over a dead end, right? It has to be one of these valid kinds of paths. Notice that you are not allowed to change. Notice you are not allowed to change any street. Okay, so you can't be like, okay, this street doesn't connect, so maybe I can flip it or whatever. Return true if there's a valid path in the grid, or false otherwise. Okay. So for this example, right, I can go from the top left to the bottom right, so it's true. And this, I start at the top left. There's actually nowhere that I can go because it's a dead end. And I can't get to the bottom right, so the answer is false. For this example, it's false because you have 1, 1, 2. So what would that be? It would be 2 of these and then 1 of these. So you'd have, a path where you can go like this. You start here at the top left. You're trying to get to the bottom right. You can go right. You can't move anymore. Okay. So for any search problem like this where there's no cost associated, you could run depth first search or breadth first search. That would be the candidate algorithm. The only thing here, though, is that, you have 4 options at any point, right? At any cell point, right? Like if I'm at this cell point here, I have 4 options in terms of where I can travel. I can travel up, I can travel to the right, I can travel down, or I can travel left. But it depends on what street I'm at and what these street values are if I can connect to them, right? If I have, now I've made this drawing here, right? If I have street 1, well, of course, for any grid cell, I can travel in any direction, right? So I can decide that I can go up, down, right, or left. I guess the first thing you notice is you can't go up, right? Because I can only connect left to right from this cell position. So I already know that this is not an option, right? I can't do this and I can't do this. I can only go left or right if I'm at this street, right? If I'm in a street 1 grid cell, I can only go left and I can only go right. And what can I connect to? Well, I can connect to another 1, right? I can go through here to the right. I can connect to a 3, right? I can connect to a 3 like this, right? I can connect to a 5 going to the right, right? I can connect to a 5 like this. I can't connect to a 6, right? Because 6 doesn't connect to this cell here. So the idea is, right, is depending on the cell that I'm at, there's different sets of cells that I can go to. Depending on the cell that I'm at, there might even be directions that I can't go in, right? I can't go up or down from street 1. So I guess what we have to do to make this problem work is we need to think about what directions we can go in which cells and what that means we can connect to next. And we can use that as a filtering criteria to determine what our neighbors are when we run BFS, right? Because when you run BFS, you have a cell and then you want to explore your neighbors. Well, there's conditions here based on who your neighbors are, right? Just because you have 4 neighbors doesn't mean you can travel to all of them. Just because you have 4 neighbors, you have to determine which of those 4 neighbors you can actually travel to next, okay? So let's go ahead and do that now. So there's different ways you can process these filters. And the way that I do it may be more confusing than the way that you're considering, but this works for me. So I'm going to think about directions and who can travel in which directions and what you can travel into, okay? So the first direction we're going to consider is right, okay? So we have this direction right. Let's move this over a little bit. So the first question I'm going to ask is who can travel right? Well, 1 can travel to the right. 2 cannot, right? Because there's no direction to the right. 3 cannot, right? Because 3 can go either left or it can go down. So we'll do right first. Okay. Who can travel left? 1 can travel left. 3 can travel left. 5 can travel left. And that's it. Okay. Who can travel up? 2 can travel up. 5 can travel up. And 6 can travel up. When I'm saying traveling up, I'm basically saying from the position that I'm in, can I leave and go up? Right? So from 2, I can go up, right? From 6, I can go up. From 5, I can go up because there's a path connecting me going up. Okay, and then the last direction, of course, is down. If I'm not mistaken, I guess this is fine. No. You know, I spend more time worrying about what color am I going to use next. Okay, down. So I'm 2, I can go down. From 3, I can go down. And from 4, I can go down. So these are the 4 directions, and these are the ways that I can go into the cell, right? Well, the next idea then is, so going right. So 1 can go right, 4 can go right, and 6 can go right. Right. So for right, we got, for our cells that we can go right, we have 1. I guess that's fine. So we have 1, we have 4, and we have 6. Now, who can be gone into from the right? Stated another way, right? When I go right, who can I connect to? Well, I can connect to anybody who can go left. Does that make sense? Right? Because I can go, if I can leave to the left, I can enter from the left. Right? So since these 3 cells I can go in from the left, that means if I go right, I can connect to them. Right? Another way of stating that, if you wanted to see a picture, right, is if I took if I took this, yeah, something's going on because I pasted on top, but it's fine. So if I take this cell, right, I can go into the right, into this cell, and into the right, into this cell. So from 1, 4, 6, the I guess if I wanted to use another color, I'll use the same color that I used for left, right? Who can I travel into? Well, I can travel into 1, 3, and 5. So 1, 3, 5, 1, 1, 3, 3, 5, 5. So from the right, at any cell, I can travel right. So what basically is saying I can travel to the right if I use the street type 1, 4, 6. And the cell's neighbor that I can travel into is 1, 3, and 5. That's what this is articulating here. Okay? Now the opposite would be true for left. Right? So who can go left? 1, 3, and 5 can go left. So 1, 3, and 5. And who can they travel into? Well, if in order for me to go left from me, if I'm going left, I have to go into the right of the cell to my left, right? If we're standing side by side, my left is your right. Right? Right. So if I'm traveling to the left, I can travel into anybody that has a left. If I'm traveling to the left, I can travel into anybody that has a right entrance. Okay? So that means I can travel into 1, 4, and 6, which are just these cells, right? So there's this corresponding relationship you should see here. So I can travel into 1, 4, and 6. All right, what are the next set of directions we have to do? So let's do up now. So who can travel up? Well, 2 can travel up, 2, 5, and 6, okay? So 2, 5, and 6, and then it's the same relationship. If I want to travel into an adjacent cell going up, then they need to be able to travel going down, right? So anybody that can travel down, I can travel into going up. So that means I can connect to who exactly? I can connect to whoever can go down, which is 3, 4, and 2. So 2, 3, 4. So 2, 3, 4, 3, 3, 2, 2, 4, 4. And then finally, the piece de resistance going down. So to go down, who can go down? Where 2 can go down, 3 can go down, 3, 4. You'll notice that this relationship is very, there's this relationship between up and down and right and left. So from going down, I have to be able to travel into someone that could go up, right? So going down, I can travel to anybody that can go up. So who can go up? 2 can go up, right? 2 can go up, 5 can go up, and 6 can go up, right here. So 2 can go up, 5 can go up, 6 can go up. 2, 5, 6, 2, 5, 6. So now we basically have a set of all neighbors, right? For any node, I can say, well, if I'm in up, then I can go up. If I'm in down, I can go down. If I'm in right, I can go right. If I'm in left, I can go left. And the neighbors that I can go into are whatever neighbors are defined for that going up, for that going down, for that going left. Okay, so we can consider all 4 directions and then consider if we can move in that direction, and then we consider if that neighbor can be moved into going that direction from where we're at. Okay, so that's basically it. So now we just need to use this idea of filtering who can travel in which direction and where they can go to address neighbors that can be explored using BFS. So let's go ahead and make this kind of dictionary sort of situation based on the directions. Okay, so I want to do this in some way so that I can, it's not gonna, the problem is, that's fine. Make it. So we'll say up equals, for each value that we can go up, we can go to, we'll make it a set, 2, 3, and 4. And which values can we do that for? We can do that for 2, 5, and 6. Right, so for 2, 5, and 6, we can go to 2, 3, and 4 next if we're trying to go up. So these are the values that can go up, and these are the next values that they can go to. Let's go ahead and just do down. Now for down, it's just swapped, right? So for 2, 3, and 4, we can go to 2, 5, and 6. All right, and then left, Left and right. All right, let's just get all this. So for left, who can go left? 1, 3, and 5. 1, and I'm just copying this verbatim from this system here. 1, 3, 5, and I can go to 1, 4, 6. And right from 1, 4, 6, I can go to 1, 3, 5. All right. All right, all right, all right. Oh, no, because that's going to... Okay. No. Dude, sometimes Apple products, the way that they decide to deal with stuff, a little frustrating. You know, it's a bit frustrating. Okay, that's fine. Good enough. Okay, so now we have that captured. So what I'm going to do... Oh, did I just mess that up? Okay. Left, I can go 1, 3, 5 to 1, 4, 6, so... Oh, something got messed up here. Ugh, man. So up, I can go 2, 5, 6 to 2, 3, 4. 2, 5, 6, 2, 3, 4. Down, I can go 2, 3, 4 to 2, 5, 6. So 2, 3, 4, 2, 5, 6. Someone was watching this and screaming at me because I did this wrong. All right, left, I can go from 1, 3, 5 to 1, 4, 6. All right, left, I can go from 1, 3, 5 to 2, 4, 6 to 1, 4, 6. And then from right, I can just do the opposite, but I'll just check it here. Right, I can go from 1, 4, 6 to 1, 3, 5. So I go from 1, 4, 6 to 1, 3, 5. All right, so now we got all the directions right. Now I'm going to run through just the standard code for BFS that you might want to copy verbatim, using a deck to allow for constant pops from the left. And then we'll alter it, right? We'll modify it slightly to accommodate for this idea of who you can travel to from where. Okay, so I'm just going to quickly speed through a Python implementation of BFS. Okay, we start at 0, 0. And then we'll say while q. So we'll pop this node. The beauty of using a deck. And then if I equals the length of grid. So basically what I'm asking here is, well, if we've gotten to this bottom left position, then we're good. In this return, there is a valid path, right? So that happens if I is at the last row and J is at the last column. Now this is an m by n, so that's the case, we return true. Right, so if we get to this final position while we're traversing the system, then we return true. What's next? Then we look at each of our neighbors, right? So what are our sets of neighbors here? Well, we have 4 neighbors that we could consider, right? There'll be some filtering later. We can go up. So this corresponds to going up. So maybe we'll consider a direction as well. Maybe not yet. So we can go up. We can go down. So we go to the next row. That corresponds to going down. We can go left. So that corresponds to going to the previous column. Or we can go right, which corresponds to going to the next column. All right, and then we have to ask, well, can we actually, is this actually a node? Are we within the boundaries of this grid? And then we have to ask if the grid is positive at this element. So what we're going to do is every time we traverse a node or we add it to our queue that we're going to traverse it, we'll set it to its negative value. So we'll say grid at 0, 0 equals negative grid at 0, 0. So this basically just encapsulates the idea of something being seen. So after you traverse a node or you add it to your queue, after you've determined that you're going to traverse a node, in order to only traverse it once, you'll set its value to the negation of itself. That way, you don't traverse it twice. So you ask, okay, if the value is negative, then this will be false, so then we won't traverse it again. Okay, so that's just a little trick to not use an additional scene array. You just set the value to its negative. That way you don't traverse the same value twice. So then you set this value. Okay, now that I've decided to traverse it, I'm going to set it to its negative. And then I'm going to need to add it to the queue so that I can traverse it later. Okay. And then at the end, what do? You return false. Because if you get to the end without this ever being true, that must mean that you've never actually traversed, you've never explored that bottom right node, right? You never traversed that bottom right grid cell. You've never been able to, so that means you were never able to reach it. So since you were never able to reach it, you exhaust all your possible options. You never get there. So you get to this statement, which means you never got there. So you return false, right? You never got there. So it's not there is no valid path to that position you're trying to get to. Okay, so this is a standard implementation of breadth first search using a deck in Python, where we're using this negation idea to note what we've already seen. That way we don't traverse the same node twice, right? We don't create some infinite loop cycle. So how do we capture the filtering aspect? Well, for the filtering aspect, how does that work? Well, for each, if I'm going I minus 1j, that means I'm traveling up. If I'm going I plus 1j, that means I'm traveling down from the current cell that I'm at. If I'm going ij minus 1, that means I'm traveling to the left. And if I'm going ij plus 1, that means I'm traveling to the right from the position that I'm in, right? Because if I'm here, right, if I'm at position ij, right, this position here is ij minus 1, right? So that's to the left. And this position here is I minus 1j, right? That's the position above, and so on and so forth. Okay? So we can look at that direction here. We'll just call it D for direction. Okay. Well, we can only travel in that direction, right, if the current street we're looking at is able to travel in that direction. Circular argument, right? So the only way we can travel in that direction is if the current grid cell's value, the negation of it, right? Because every time you traverse a node, you set it to its negative. So if the negative of the current grid cell that we're at, we're basically saying, is this in the direction that we're trying to travel? Right? At the current grid cell that I'm at, the value of the current grid cell that I'm at, the negation of it, because we set it to its negative when we traverse it. So if we negate again, we get the initial value. So is that in the direction that I'm trying to travel, right? If the street value is 1, right, that means that it's in left and it's in right, but it's not in up or down. So I'm basically saying, from this cell, can I even travel in that direction? Okay, so that's what this is asking. And then the next question would be, and now we're going to delete this, and I'll explain why in a second. So can I even travel in that direction from the current cell that I'm at? That's this first question. And I guess we'd have to ask, okay, so let's move this over here. So let's first check that they're valid. And can I, what? Can I travel to the subsequent cell, right? Can I travel to the subsequent swell? Will that subsequent cell even allow me to travel into it? Swell. So from street 1, I can travel left and right? So that's good if the direction is left or right. But I can't travel into all the other streets going left or right. So I have to check if I can even travel into that cell from my current cell in the direction that I'm trying to go. So can I travel to, is the grid cell KL, right? Can I travel to that cell type? Can I travel to that street type from the cell that I'm trying to go to in the current direction? Okay. So what this basically means is, can I travel in this direction from the grid cell? That's what this statement's asking here. Can I even travel in that direction? Okay, if I can travel in that direction, then it'll ask this question. If I can travel in that direction, can I even travel into this subsequent cell in that direction, right? If I'm traveling in that direction into that subsequent cell, in that neighboring cell, does it have a connection type such that I can enter into it? All right. Now, the reason why we got rid of the grid cells value -0, because if this is negative, then it'll never be in D, right? So if it's negative, that'll just note that we've already decided that we're going to traverse the cell. So we don't need to worry about that. Okay. So that will filter the neighbors. And I think that that will fix this code, right? That'll address these street types. We'll see. There's probably a little bit of issue because we're doing a lot here. That's never what you want to see. Okay. Oh, this got, the negative of that got removed somehow. Whew, I was worried there for a moment. Come on. I guess that's okay. I don't know. The solution's fine. I don't know why it's doing that. All right, I got a much faster runtime before. This runtime is fine. You know, this is the optimal solution, I believe. Maybe there's like a dynamic programming program. No, it would be the same. Okay, so whatever. So when we're looking at this, what is the runtime and the space? This is so massive, it's crazy. I don't know why I did that. Now I'm tiny. All right, so creating this is constant time, constant time, constant time, constant time, right? Because I'm just taking, just, you know, pre-computing these. It doesn't matter in terms of the size of the grid. We'll have to look at each cell at least once, right? So we look at each cell at least once and make a decision about the neighbors to add to the queue. But that's never going to be, we're never going to look at each cell more than once, right? So if M equals, if M equals the length of the grid and N equals the length of the number of columns, right, or whatever, time's going to be big O of Mn, because we just look at each grid cell at least once, right? So while the queue, we're going to have to look at most every, not at least, at most we're going to have to look at every grid cell. And then we just do a constant check, right? This is a constant operation, constant operation. All these are constant operations. This is 4 constant operations, right? Because we look in each direction, right? But it's not going to be no bigger than looking at some constant operation, constant set of operations multiplied by every grid cell we have to look at. And then for space, let's see, it's a little tricky. I hate dealing with space here because we create this queue and we have to add all the neighbors of each neighbor. So it could get no bigger than O of Mn. There might be a tighter boundary, I'm not sure, but you know, we might have to add all of our neighbors to the system. So that's one way of looking at it. Okay, peace out, guys.